Welcome back to VLSI and chip design. In this lecture video, we are going to see about CMOS logic, inverter, NAND gate and NOR gate. Before entering into that, we have to know what is an inverter. We already know inverter is nothing but an NOT gate. So CMOS inverter is otherwise called as an NOT gate. Here we are using one NMOS transistor and one PMOS transistor. The bar at the top indicates VDD, that is PMOS transistor is always connected to VDD and NMOS transistor is always connected to ground, and the input to the PMOS and NMOS is given at the gate terminal and output is taken at the center of the PMOS and NMOS, and it is denoted by Y. And we know the truth table of the inverter. When we are giving an input to be 0, the output produced will be 1, and when we are giving the input to be 1, the output produced is 0. This is the basic truth table behind the inverter. Next, we are going to see about inverter operation. When the input A is 0, the NMOS transistor is off and PMOS transistor is on. Thus, the output Y is pulled up to 1 because it is connected to VDD but not connected to ground. Conversely, when we are giving an input to be 1, the NMOS is on and the PMOS is off and Y is pulled down to 0. This is the operation behind the inverter. Next, we are going to see about logic diagram for Boolean expression. Before entering into that, we have to remember a hint. Suppose if a Boolean expression is given in a product form, for example, A dot B. So, when it is given as A dot B, PMOS should always be connected in parallel and NMOS should always be connected in series when it is given in product form. Suppose when the Boolean expression is given in a sum term, that is, for example, it is given as y equal to a plus b, that is sum term. During that time, PMOS is always connected in series and NMOS is always connected in parallel. So this is the basic hint we have to remember before drawing the logic diagram for the Boolean expression. And next thing we have to remember is PMOS is otherwise called as pull-up network and NMOS is otherwise called as pull-down network. To both the input, that is to both the PMOS and NMOS, we are giving the input and output is taken at the center of PMOS and NMOS. Next, we are going to see about one basic example. That is, we are going to see a NAND gate, expression of the NAND gate. The figure shows two input CMOS NAND gate, that is, it consists of two series NMOS transistors between Y and ground and two parallel PMOS transistors between Y and VDD. We know that the output of NAND gate is Y equal to A dot B, the whole bar, and this indicates that it is in product form. When it is in product form, we have to connect the PMOS in parallel manner and NMOS in series manner. So we have connected two PMOSs in parallel manner and this two PMOSs is connected to VDD, and next two NMOSs is connected in series manner and this two NMOSs is connected to ground, and the input is given to one PMOS and one NMOS, that is A, and another input is given to second PMOS and second NMOS, that is B, and the output is taken at the junction of two PMOS and NMOS, that is Y. And the truth table for this is given here, that is when both the input, that is A and B, is 0 0, the pull down network, that is NMOS transistor, is off and pull up network, that is PMOS transistor, is on and the output is 1. And the next thing is when we are giving 0 and 1 as the input, the pull down network is off and pull up network is on and the output produced is 1. And the next thing, we are giving the input to be 1 and 0, the pull up network will be off and pull down network will be off and pull up network will be on and the output produced is 1. And when we are giving the input to be 1 and 1, the pull down network will be on and pull up network will be off, that is the output will be 0. This is the basic thing behind the truth table and the CMOS inverter for the NAND gate. Next, this is the condition we have applied here, that is 0 and 1. During that time, one PMOS will be off and one PMOS will be on. Similarly, one NMOS will be off and another one NMOS will be on. This is 0 1. When we are applying 0 1, this is the condition produced and the output produced will be 1. And in next, when we are giving 1 0, the one PMOS will be on and second PMOS will be off. And similarly, first NMOS will be on and second NMOS will be off condition and the output produced is 1. This is the third operation and the last operation here is 0 1 1. That is, we are giving the input to be 1 and the output obtained is 0 here. During this time, both the NMOSs will be on and both the PMOSs will be off. So the output produced is 0. So this is the final summary of NAND gate operation. If either input A or B is 0, at least one of the NMOS transistor will be off, taking the path from Y to ground. But at least one of the PMOS transistor will be on, creating a path from Y to VDD. Hence the output Y will be 1 if both inputs are 1. Both of them NMOS transistor will be on and both of the PMOS transistor will be off. Hence the output will be 0. Thank you.